today we're going to start with Module 2, and we're going to do Lessons 1 and 2. I've changed it a little bit, streamlined it a little bit. There's fewer assignments, so that should make it a little bit easier on you. And I've eliminated soft chalk and put it in all the information into pages, so you go right through Canvas and it should be easier. It shouldn't tell you you're not allowed to do stuff. So in the very first module, what they're looking for is to design a model. And what the model is going to do is it's going to describe what is happening with the electromagnet and the metal in a scrapyard. They want to know how is this metal being picked up, and they want you to create a model. And our assignment for Lesson 1 is we're going to do a discussion board. We're going to draw our model. We're going to put it up there. And remember, you need to comment on 2 other people's models. A lot of us did a really good job with the model and why it was happening and what it was doing, but we forgot to comment on other people's models. So make sure you do that. That's part of your grade. In the second lesson, they start to talk about magnetism. The first part of the lesson, they go through and they give you a list of things, and they ask you what would be magnetic and what would not be magnetic. What things would you be able to pick up with a magnet, and which things would you not be able to? As you go through the list, it looks kind of easy, but as you go through, not all metals are magnetic. Some of these metals will be picked up and some of these metals won't be picked up. So as you look at this, you know a plastic button is definitely not going to be magnetic. You know a glass is not going to be magnetic, but it gets a little more tricky when you get to the different kinds of metals. So they do have some practice for you and help you out. Make sure you take a look at what kinds of metals are magnetic and which ones are not magnetic. So they're going to give you to describe a lab for you guys, and they want to talk about the strength of magnets, and they want to test 2 different things: the distance versus strength. So what they ask you to do is take 10 paper clips, and they want you to line them up. They want you to put them at the 0 mark of a ruler, and then they want you to take your magnet and put it at 10, 8, 6, 4, 2, and then 0. And what they want you to do is find out how many paper clips the magnet will attract. So you're going to make a data table and record your data. And I used 2 different kinds of magnets to show you guys. This is a ceramic magnet, and it's a little bit stronger than the bar magnet. So that gives you an idea how to do it. If you do not have magnets at your house, it's not really a problem. You can watch the video again and you can record data. Set up a data table, something like this. This is not in your Canvas. This is just something you're going to design on your own. And you can look and see when the magnet started to engage the paper clips and how many it engaged. The next thing you're going to do is they give you a simulation. It's from Colorado, University of Colorado, and it's a simulation. And what it does is it shows you what a compass is going to do when it comes near a magnet. So this one I had trouble opening up on my computer. What I had to do is I had to put in FET magnets compass. If you type in FET magnets compass, it'll show you this. And what you could do is you can move the magnet around and you can watch what all these little tiny magnets do, but you can also watch what the larger magnet does. So I put it in a couple different places for you guys to take a look in case you can't get the simulation open. I put it right beside the magnet on both sides, with the south pole towards the compass and the north pole towards the compass, so you can see how they're different. I also placed it above, with the south on my left and the north on my right, above and below the magnet, to see how the compass changes and how all the little compass arrows change. So what we were seeing in the simulation, we were seeing that there were different poles marked north and south. Magnets have poles, the earth has a pole. They're both magnets. So if I put a north pole to a south pole, opposites attract. But if I put like poles, like a north pole and a north pole, they're going to repel, and a south pole and a south pole is going to repel. It's called the law of magnets. If you look at the Earth, where we think the North Pole is, it's actually the South Pole of a magnet. and wherever the south pole is would be the north end of the magnet. So the magnetic poles are actually reversed in what we call them in geography. Okay, so we know that magnets can push or pull, and we said that anything that pushes or pulls is a force. So a magnetic field is a force. If you look at it carefully, you notice that it's coming out, the arrows are coming out of the North Pole, and then they come back in the South Pole, so they're directional. It makes a difference. If you have a North Pole or South Pole of a magnet, they're going to act differently. So when I have a magnet and I sprinkle iron filings, which are small pieces of metal, over the top of a piece of paper, I get a pattern. And what that pattern is doing is it'll show me all the different lines of force that that magnet has. So an invisible field that we can't normally see, we can see when we have iron filings. The other way they showed us is when we did this in our simulation. Instead of using iron filings, they used a little tiny compass. And when the compass will point, and you can also see the lines of force. Right? You can see them coming up out here, down here, and around here. And they will look similar to the iron filings. The advantage of having the small compass is they will tell you which direction they're going. They'll tell you which is north and which is south, where the iron filings you can't tell. These are marked, but that's written on there. That's not in iron filings. So when I take two opposite sides, we said that opposites attract. And when opposites are attracting, there's going to be a force that goes between them. And as I separate these, as I move these apart, as this yellow arrow would get longer, I'd have more and more potential energy. In the last module, we said that kinetic energy and potential energy convert back and forth. So if I have higher potential energy, I have lower kinetic energy. So as I move these magnets closer and closer together, I increase the kinetic energy and decrease potential energy. The exact opposite is true when I have two of the same poles. If I have north and north, or if I have south and south. As I push them closer and closer, there's going to be more potential energy and less kinetic energy. As I move them farther apart, I'm going to increase kinetic and decrease potential energy.